Lesson 13-2, Simplifying Radical Expressions. And in this lesson, you learn to simplify square roots and to simplify radical expressions. Okay, so let's take a look at this example in physics. The period of a pendulum is the time in seconds that it takes the pendulum to make one complete swing back and forth. Okay, so that's one period of the pendulum, the time it takes it to make one complete swing back and forth. So the formula for the period of a pendulum is equal to P is equal to 2 pi times radical L all over 32, where L is the length of the pendulum in feet. And suppose a clock makes one tick after each complete swing back and forth on a 2-foot pendulum. How many ticks would a clock make in 1 minute? So we're trying to find the period in a pendulum in 1 minute. Okay, so we'll solve this in example 4. And before we do that, okay, can 2 pi times radical L over 32 be simplified? So again, one rule used for simplifying radical expressions, okay, we know that, is that a radical expression is the simplest form of the radicand, okay? So the expression under the radical sign, so basically your radicand is the expression under the radical sign. So the expression under the radical sign, and then it is also, it should not contain any perfect square factors other than 1. Okay, so let's recap that. So if you want to simplify radical expressions, okay, a radical expression is in simplest form if the radicand, this one right here, the expression under the radical sign, contains no perfect square factors other than 1. The following property can be used to simplify square roots. And this is the property we're going to use. And this property is called the product of square roots. And the product of square roots simply states that for any numbers a and b, where a is greater than or equal to 0 and b is greater than or equal to 0, okay, the radical ab is equal to radical a times radical b. So the product property of square roots and prime factorization can be used to simplify radical expressions in which the radicand is not a perfect square. So if you have radical 18 and you want to simplify radical 18, we simply first get the prime factorization of 18. So we get radical 18, copy the problem, okay? And one way to do that is do the drop down method. First prime number that goes into 18 is 2. 18 divided by 2 is 9. First prime number that goes into 9 is 3. Okay, so you have 2 times 3 times 3. And if you notice, since we're talking about a square root, okay, remember, this is a square. And let's say the area is 4. And that means the side would be equal to 2 and 2. Okay, the root of this square is 2. When you pair up that 2, the root of that square would only be 2. So using the drop down method, the root of 9, okay, the square root of 9 would be 3. Okay, and we simply bring down that 2. Okay, so knowing that, the prime factorization of 18 would be 3 times 3 times 2, or with this radical 3 times 3, or 9 times radical 2, which is the same as 3 radical 2. So in this case, when you're doing the drop down, you simply pair up the two numbers that are the same. So in this case, it's 3, and that goes out of your square root. And the numbers that don't have pairs, okay, that don't pair up, goes inside your radical sign. So you can see two ways of doing this. And let's take a look at B, okay? And in B, so a radical 140, okay? Again, let's do the prime factorization method. So 140, okay? Radical 140 using the drop down method, okay? 140 divided by 2 is 70, divided by 2 is 35, divided by 5 is 7. So this is actually radical 2 times 2 times 5 times 7, or this is actually 2 squared times 5 times 7, radical that is, okay, or this is simply 2 radical 35. So if you look at the drop down method, you simply pair up the 2 and that goes outside, and these two numbers, prime factors, don't have any pairs, so you simply keep them inside. 5 times 7 will give you 35. So this is another way of finding the square root, the drop down method or the prime factorization method. Both methods will work fine. Okay, and let's take a look at principal square roots. Remember, when finding a principal square root of an expression, okay, containing variables, be sure that the result is not negative. So when you talk about the principal square root, okay, let me give you an idea what the principal square root is. When I say the square root of 9, so the answer might be positive 3 or negative 3. Why? Because negative 3 times negative 3 is 9, positive 3 times positive 3 is 9. And that's the reason why there are two answers. But when you're referring to principal square root of 9, we're only getting the non-negative value. Okay, and that's the reason why it's here. So when finding the principal square root of an expression containing variables, be sure that the result is non-negative, and that's what it's saying there. So consider the expression x squared. In simplest form, x, its simplest form is not x, since, for example, radical negative 4x squared is not equal to 4. So for radical expressions like radical x squared, to make sure that you don't get negative results, okay, we do this. So when you have x, the radical x squared, you will put an absolute value sign. So the absolute value of x. When we get the absolute value of x cubed, this is simply absolute radical x squared times x. So we still get the absolute value of x times radical x. Radical x to the fourth is x squared, okay? Because even if it's negative, if you square it, it becomes positive. And radical x to the fifth power, okay, is simply x squared times x, okay? And radical x to the sixth is the absolute value of x cubed. So it's important to memorize these scenarios so that when we start simplifying radical expressions, you know what to do. Okay, so for one more, for radical x cubed, absolute value is not necessary. Okay, so if x were negative, then x cubed would be negative, and x cubed would not be defined as a real number. So remember, anything that's inside the radical sign that's negative is not considered to be a real number, and you learn later on they are called imaginary number. So why is absolute value not necessary for x to the fourth? Okay, that's a good question. Why is absolute value not necessary for x to the fourth? Again, okay, you're raising it to an even integer, so therefore when you square it, even if it's negative, it will still continue to be positive. Okay, so let's use all of these to look at example number 2. So in example number 2, we want to simplify radical 72, x cubed y to the fourth, z to the fifth power. So first things first, we copy it down, okay, and we get the prime factorization of 72, which is 2 cubed plus 3 squared, and we simply copy down x cubed y to the fourth is z to the fifth power. And then we break it down. We know that 2 cubed, according to our rule from the last slide, is actually 2 squared times 2, okay, and 3 squared times x squared times x, okay, and you have y to the fourth times z to the fourth times z, okay. Now how did this happen? Let's go back to the last slide, because if you look at this one, x cubed is nothing more than radical x squared times radical x. X to the fourth is nothing more than x squared times x, radical x squared times radical x squared, and x to the fifth is x to the fourth, radical x to the fourth times x, radical x. Okay? So those are a little bit of the shortcuts there. And if you look at the absolute value of, the radical x to the 6 is the same as radical x to the fourth. Okay, sorry, erase that. Radical x to the fourth times radical x squared. Okay, and we know that radical x to the fourth is x, right? But this is absolute value of x. Okay, sorry, this is x squared, and this is the absolute value of x, and therefore x squared times the absolute value of x will give you absolute value of x cubed. And that's how this came about. Okay, going back again. Okay, copy that down, and you break it down to this. And from there, we use what we learned in the last slide. Okay, so radical 2 squared is 2. Okay, times 3, which is radical 3 squared, multiplied by radical x, because it's absolute value of x coming from radical x squared, and you have y squared coming from radical y to the fourth, and z squared coming from z to the fourth. Okay, everything else is not a perfect square, so we leave them inside a radical sign, which is 2, x, and z. And we simply multiply them again, combine them. You have 6 times radical x, 6 times the absolute value of x times y squared times z squared times radical 2x z. So the absolute value of x ensures a non-negative result. Okay? So, again, on example 3, the product property can also be used to multiply square roots. If you want to simplify radical 5 times radical 35, okay, copy the problem. You can say that radical 5 is the same as radical 5 times radical 7. Again, the property of square roots. Okay, and then you can combine radical 5 times radical 5 to become radical 5 squared times, okay, radical 7. So they just forgot to write down radical 7 here, right there. And then that becomes 5 times radical 7. Okay, so again, we're getting the principal square root of 5 squared, which is 5. Okay, and finally, in the last example, example number 4, we are going back to the beginning of the lesson. And before we do that, the secret word for this particular lesson is turbo. The secret word is turbo. So refer to the connection at the beginning of the lesson. How many ticks would the clock make in 1 minute? And we will use 3.144 pi, round to the nearest whole number. So first, we look at the explore. What we know, the clock makes 1 tick after each complete swing back and forth on its 2-foot pendulum. Okay, so the formula for the product P of the pendulum is equal to 2 pi times radical L over 32. Okay, so how do we plan to solve this? First, we want to find T, the number of seconds it takes for the pendulum to go back and forth 1 time. Okay, then find 60 over P, the number of times the clock's pendulum swings back and forth in 1 minute. Okay, so now we have a plan. Let's implement that. So first, write down the formula. P is equal to 2 pi times radical L over 32, which is approximately equal to 2 times 3.14, approximate value of pi, times radical 2 over 32, which is 2, the length of our pendulum. And then we simplify 2 over 32 to become 1 over 16, and 2 times 3.14 as 6.28. Then we now have 6.28 times 1/4, because this is actually the square root of 1 over 4 times 4. Okay, that's the reason why it became 1/4. Or 1.57. So it takes about 1.57 seconds for the pendulum to go back and forth once. Okay? And then get that 1.57 and divide it by, and get that 1.7 and let it be your divisor for 60, which will give you 32.22. Thus the clock makes about 38 ticks per minute. Okay? And if you want to check if our answer makes sense or not, okay, you simply substitute, or you simply multiply 38.22, okay, and multiply it with 1.57, and you'll find out when you multiply it, okay, you'll end up with 40 times 1.5. It's about 40, round this to 40, and round this to around 1.5. Okay, it's about 60, so the answer is pretty much reasonable. So the product of this is approximately 60, so we know that it's pretty much reasonable. Okay, so let's go to the next concept of this, which is the quotient property of square roots. For any numbers a and b where a is greater than or equal to 0 and b is greater than 0, radical a over b is the same as radical a all over radical b. Okay, so let's take a look at a. Radical 56 over radical 7, okay, and radical 34 over radical over radical, okay, 7. So using letter A, you have radical 56 over radical 7. That will be equal to just one radical sign, 56 over 7, which is the quotient property of square roots, and 56 over 7 is actually radical 8. And if you simplify radical 8, remember radical 8, okay, you get the drop down 2, 4, and 2. Pair that up, that's your 2, that goes out your radical sign, and this one doesn't have a pair, so it's 2 radical 2 right there. Okay, and we want to simplify letter B. This is actually example 5 in your book. I don't know why I didn't write down the example. So in example number 5, you have radical 34, okay, over radical 25. So radical 34 over radical 25 is actually radical 34 over radical 25. So you have a radical 34 over 5. 5 is the principal square root of radical 25. Okay, so 5 is the principal square root of 25. And that is the simplest form. Okay, without going into decimals, of course. So in letter B, we want to compare the expressions using greater than, less than, or equal to. Okay, so we can compare these expressions, the next slide right here, by estimating their values and then using a scientific calculator to find approximations for each simplified expression. So first, let's do some estimating. We estimate that 2 radical 2, since 2 is a little more than 1, 2 radical 2 will be a little more than 2. Okay, so we now have radical 34 over 5 is approximately radical 36 over 5. So because 34 is the nearest square number to 34 is 36. So we now have 6 over 5. So radical 34 over 5 is approximately close to 6 over 5. Okay, so this will be a little more than 1. Okay, so if you notice, 2 radical 2 is greater than 2 radical 2 is greater than radical 34 over 5. Okay, and if you verify this using a calculator, you have 2 times 2, and then you punch radical x, that'll be 2.8, and 34, punch those numbers in a calculator, it'll give you 1.166. So if you notice, 2 radical 2 is definitely greater than radical 34 over 5. Okay, Okay, let's move on because there's going to be a lot more on this. So we know for a fact that since 2.8 is greater than 1.2, we know that radical 56 over radical 7 is greater than radical 34 over 25. Okay, so that's the end of that example. Okay, and let's talk about rationalizing denominators for radicals. So in the cartoon above, let's see if there's a cartoon below here. No, there is none. So if you look at your book, okay, there's a cartoon, and if you open it to page 722, it says there, you're lucky. In the Peanuts cartoon, you're lucky. Do you know that the bird, you're lucky because you don't have to study math. You didn't have to know about rationalizing denominator and dumb things like that. So I'm just reading in the cartoon. So you're really lucky. Okay, and then I don't know the name of this bird, but she starts thinking about rationalizing denominators. Okay, which is actually correct. Okay, so in the cartoon above or in your book, Woodstock, oh, her name's Woodstock. Woodstock simplified the radical expression by what we call rationalizing the denominator. This method may be used to remove or eliminate radicals from the denominator of a fraction. Okay, so when we simplify a radical expression, it's only simplified when there are no radical signs in the denominator, and we do this by rationalizing the denominator. So if you have radical 5 over radical 3, first copy the problem, radical 5 over radical 3. To be able to remove the radical sign, we do radical 5 over radical 3, and we multiply it by 1. That will not change our fraction. Okay, again, the identity property of multiplication. So how do we do that? We simply multiply it by radical 3 over radical 3. So if you notice, if I multiply radical 3 times radical 3, this becomes radical 9 or simply 3. And this becomes radical 15. Okay? And so this is how you rationalize this denominator. Radical 5 over radical 3 in simplest form is actually radical 15 over radical 3. And let's take a look at the next example, radical 7 all over radical 12. Again, copy the problem, radical 7 all over radical 12. Okay, and from there, we rationalize the denominator. But before we rationalize the denominator, we need to simplify radical 12. And we know that radical 12, using the step down or the drop down, 2, 6, 2, 3, pair that up, that's a 2. So this becomes 2 radical 3, so that goes in. So this becomes now 2 radical 3. All we need to do is rationalize radical 3. Again, we multiply it by 1, which is radical 3 all over radical 3. Okay, so from there we now have radical 7 times radical 3 all over 2 times radical 3 times radical 3 is 3. So this is radical 21 all over 6. Okay? This is the easy stuff in rationalizing denominators, and this is where our factoring comes in the next concept, in the next slide. So binomials in the form of a times radical b plus c times radical d and a times radical b minus c times radical d are called conjugates. And if you notice, this looks like something that we did in factoring, which is a plus b and a minus b. Okay, this looks very similar to difference of squares, and remember, in difference of squares, what do we get? Is a squared minus b squared. So conjugates are very similar to difference of squares, remember that, okay, as we go through this. So a radical b times c plus c radical d and a radical b minus c radical d are called conjugates because of our difference of squares. For example, 6 plus radical 2 and 6 minus 2 are called conjugates. Okay, conjugates are useful when simplifying radical expressions because their product, okay, is always a rational number with no radicals. That's the reason why we do this, is because once we get the product of the conjugates, okay, it's always a rational number with no radicals. So if you get 6 plus radical 2 times the quantity 6 minus radical 2 using a difference of squares, that's the same as 6 squared minus radical 2 squared. And this becomes 36 minus 2, or simply 34. Okay, so again, this is your pattern right here, difference of squares, to simplify the product. Okay, so the product of the conjugate of 6 plus radical 2 will be 34. Okay, so this is true because of the following. We know for a fact that radical 2 squared is the same as radical 2 times radical 2, or it's the same as radical 2 radical 2 times 2, or simply radical 2 squared, or 2. Okay? Okay, now let's use conjugates to rationalize our denominator. So we want to simplify 4 times radical 3. Okay? So again, to rationalize this denominator, multiply both the numerator and denominator by the conjugate of 4 minus radical 3, which is, okay, 4 plus radical 3. So if you multiply both of them by its conjugate, 4 plus radical 3, okay, right here, we first copy the problem, right here. And then we multiply 4 all over 4 minus radical 3 by 4 plus radical 3 all over 4 plus radical 3. Again, this is equal to 1. Okay, look what happens. We now have, right here, use the distributive property. That's why you have 4 times 4 and 4 times radical 3. And this is your difference of squares. So you now have 4 squared times radical 3 squared. Okay, so from there, you end up with the numerator, which is 16 plus 4 radical 3. We simplified 4 times 4. And then this becomes 16 minus 3 because that's 16. And radical 3 squared is 3. So you end up with 16 plus 4 radical 3 all over 13. Okay? And that is how you rationalize your denominator by using conjugates. Okay? Now, I mentioned this a little while ago, but to be able to, okay, when simplifying radical expressions, check the following conditions to determine if the expression is in simplest form. So these are the conditions that will tell you that the expression, okay, a radical expression, is in simplest form. First, okay, no radicals have perfect square factors other than 1. Second, no radicals contain fractions. And finally, third, no radicals appear in the denominator of the fraction. So with these three, okay, if these three conditions are met, okay, your radical expression is in simplest form. No radicals have perfect square factors other than 1. No radicals contain fractions, and no radicals appear in the denominator of the fraction. Okay? And that's our lesson. Thanks for watching.